Hello friends, welcome to the lecture series of this oscillation. Now today we shall discuss the solution of differential equation of motion of the simple harmonic motion. Okay, so let's start. Now as you know, this is the second order linear differential equation of a simple harmonic motion that we discussed in the last class. Now to solve this, what you have to do, you have to consider a trial solution. Now here we are considering the trial solution is a e to the power lambda t. So here t is the variable, so you have to consider the variable here, and lambda is the root of this second order differential equation. Now as it is a second order differential equation, you will have two lambdas. If you have three dimensional differential equation, means third order differential equation, then you will get three values of this lambda. Lambda will be of three values. Okay. Now let's see. So we are considering x equal to a e to the power lambda t. Now what you have to do here, it is second order differentiation of x with respect to t, right? So first we have to take the first order differentiation of x with respect to t. So it will be lambda a e to the power lambda t. You know this. Now let's do the second order differentiation, d2x dt2. So again another lambda will come out and it will be lambda square a e to the power lambda t. So it will be lambda square x. Okay, now let's put it here. So it will be lambda square x plus omega square x equal to 0 and lambda square equal to minus omega square. So lambda will be basically plus minus I omega, where I is the imaginary number. Now you can see, as I told, as it is second order differential equation, you should get two roots and we are getting two roots. If you have third order, then three roots you will get. If it is first order, you will get one root. Okay, so there are two possible solution of this equation, that is x equal to a e to the power I omega t. So plus I omega t we have to consider once, and another one is x equal to a e to the power minus I omega t. And the general solution, to get the general solution, what you have to do, you have to add these two solutions. So once we are considering a1, another is a2 for this case. Now you know e to the power I omega t, if you consider e to the power I theta, then you know that is cos theta plus I sin theta, and it is e to the power minus I theta, that is cos theta minus I sin. Now if we add these two, it will be a1 plus a2 cos omega t, and this is I a1 minus a2 sin omega t. Now let's consider a1 plus a2 is a1 and I a1 minus a2 is a2, and if we consider a1 equal to a sin phi and a2 is a cos phi, then we will get the solution x equal to capital A sin omega t plus phi, where phi is this tan inverse a1 by a2. Okay, and a will be root over a1 square plus a2 square. So this is the wave equation. This solution we are getting from here, and this is called the wave equation of this simple harmonic motion. Now let's see how we can relate the simple harmonic motion with a circular motion. So let's start from this O point. So this is the starting point of the oscillation. Okay, so here how you will relate. So for this, for a particular position, you consider this P point. Okay, P point. So from here, so basically we have to take the projection on this y axis from P. So the height from this point, the center, that is y. So y will be a sin omega t. So y by a is sin theta. Y by a is sin theta. So theta, you know, that will be omega t. The omega is the angular frequency here. So that will be sin omega t, and we can write y equal to a sin omega t. So there is no phi. Phi is the initial position. Here we are considering the position of the bob is at the mean position. Okay, if it is displaced by some angle, suppose phi angle, then you have to add that phi, right? That is the phase difference. Okay, so how we can relate here? From the figure you see, oh, here we are starting from O, from here, so it is rotating in anti-clockwise direction, right? So it is going at q is here, that is the maximum amplitude. Then r is here, again you are coming to the mean position, then in the opposite side, that is s here, and then again in this point. Okay, now what I was telling, that if the bob of the pendulum is displaced by some angle phi, so this is the initial angle, this is the phase, initial phase, so that we have to add up, right? So from the mathematics also we can see here, this will be sine theta plus phi, and that will be omega t plus phi. So this solution we got here also by mathematics. If we solve this differential equation, we can reach here. From this picture also we are getting the same solution. So today I am ending here. So see you in the next class. Thank you.